Hi, I'm Marios, and together with Paris, Vasya, and Asterios, we present the tutorial Beyond Analytics, the Evolution of Stream Processing Systems. The aim of this tutorial is to reflect on the evolution of stream processing systems, educating the audience on the system's core aspects, and provide a forward look into the future applications of streaming systems. This is the fourth part of the tutorial, and is devoted in fault recovery and high availability. We will first examine fault recovery to establish the basic notions and approaches, and then proceed to high availability. The discussion will follow the same structure for each of the two concepts. We will first provide a definition, then present the main approaches, and finally we will highlight the main challenges as well as ways to overcome them. We begin with fault recovery. Entering fault recovery, as promised, we will discuss what fault recovery means, which are the main approaches to fault recovery in streaming today, and the challenges related to each approach. If we were to ask what fault recovery intuitively means, we could say that it regards how to recover from a failure as if the failure had never happened. This definition follows closely the standard definition of fault tolerance, and the only reason we don't use the term fault tolerance is to narrow the discussion to the part of recovery, leaving out aspects such as failure models and ways of diagnosing failures. The definition makes it clear that a strict notion of consistency is considered, which entails that a failure is completely masked and that the system is reinstated exactly to the state it was prior to the failure. In fact, this is a continuation of the tutorial's part on state management, where Paris painted a beautiful picture of the evolution of state in streaming systems, zooming also in the processing guarantees that systems offer. Notably, the guarantees are only endangered when failures happen, as any reasonable system can be consistent on a sunny day. Thus, as the evolution of state, which is key in fault recovery, has been covered in the previous tutorial part, we will focus on how to take the processing guarantees a step further for achieving this notion of consistency. This continues to be a main challenge in fault recovery. But first, let's look at two of the main approaches that streaming systems use to apply fault recovery. These are checkpoint-based recovery, which persists the system state, and lineage-based recovery, which persists the state's updates. Each of the two approaches is based on the premise that keeping the current state or the state's updates, respectively, is more efficient in computational terms. The answer to which one is better is that it depends on the workload characteristics. The Apache Samza paper includes an analysis on this aspect. Unsurprisingly, in between the two approaches, there are many possibilities that are also adopted in streaming. Checkpoint-based recovery entails that stateful operators checkpoint their state periodically in a coordinated manner, as Paris showed in the state management part. Notably, it is assumed that the input sources are replayable, like Apache Kafka, and can be instructed to provide input from a specific offset. The offset is also part of operator 1's checkpoint. Coordination is achieved by injecting a checkpoint marker in the data stream from operator 1 that propagates the data flow graph. The checkpointed state of all operators captures the system's global state. Once a checkpoint is complete, the checkpointed state of each operator is transferred to resilient storage, for instance, a distributed file system such as HDFS. Now imagine that between the second and third checkpoint, a failure happens that kills operator 2. When a new operator instance operator 2 prime is started in the right figure, it reads from the resilient store operator 2's latest checkpointed state, which corresponds to the second checkpoint. Operator 1, who had been processing tuples of the epoch following checkpoint 2, also rollbacks its state to checkpoint 2. Finally, as you can see in the left figure, operator 1 starts to receive tuples from sources from the offset it recorded in checkpoint 2, reprocesses them, and sends the output tuples to operator 2 prime. By the way, the figure order, left-right, right-left, is the same throughout this part of the tutorial. This checkpoint-based approach closely resembles Apache Flame's fault recovery approach. IBM Streams follows a similar checkpoint-based approach. Apache Spark's approach, as per the structured streaming paper, also uses checkpoints but with some differences. A second line of approaches rely on recomputing state based on state updates, that is the lineage of state. In the same data flow graph as before, imagine that operators 1 and 2 do not take checkpoints, but instead send state updates to resilient storage in batches asynchronously. Then at some point, a failure happens that kills poor operator 2. When a new operator instance, operator 2 prime, is started in the right figure, it reads from the resilient store operator 2's state updates in order to rebuild its state. Operator 1 also has to roll back its state in order to provide operator 2 prime with the tuples it has missed. But since a checkpoint is not available, operator 1 has to empty and recompute its state up to the last batch of updates from the changelog. Finally, operator 1 starts to receive tuples from sources, starting from the tuple it recorded in the last batch, reprocesses them, and sends the output tuples to operator 2 prime. This design may not correspond to an existing system, but it serves as a design archetype that reflects a pure lineage-based approach. That said, Apache Samza implements a purely lineage-based approach, but in Samza each task, that is the unit of execution, runs the entire graph of operators, so all operators are local to a task, thereby limiting task interactions. Thus, recovering a task typically requires rebuilding its state and asking for input data to be replayed from the desired offset. Apache Spark's previous approach, as per the discretized streams paper, combines checkpoints with lineage to recompute state after the loaded checkpoint. Following the brief presentation of those two main approaches, there is one challenge that is common across them. It regards consistency. In the state management part, Paris explained the processing guarantees and the level of consistency they provide with respect to the system state. However, undoing effect is not possible in general outside the system's boundaries, and thus, any output provided by the system to external applications cannot be rolled back like its state. The problem of providing an output exactly once to the outside world is well known in the distributed systems community as the output commit problem. In streaming, a few solutions have been provided, but usually the problem is not mentioned, or it is only mentioned as a concern, or it is dealt with in passing, with a few exceptions such as the Millwall paper and a few more especially in the early years of streaming, such as the Flux paper and the seminal paper on high availability algorithms for distributed stream processing. So we will define the output commit problem, look at how streaming systems solve it, and list the assumptions their solutions make. The output commit problem specifies that the system should only publish output to the outside world when it is certain that the system can recover the state from where the output was published, so that every output is only published once. In other words, a system has to record the output it publishes to the outside world so that it can recover the state if need be and not send the same output twice. If output is sent twice, then the system manifests inconsistent behavior with respect to the outside world. A typical instance of this problem manifests when a system is restoring some previous consistent state due to a failure. Other terms that refer to the same problem are processing output exactly once and its paraphrases, as well as precise recovery and strong productions. Let's see an example. We have the same data flow graph as in the checkpoint-based approach. Two sources provide input, two operators process tuples and take periodic checkpoints that are recorded in a resilient store, and two sinks receive the streaming job's output. In the left figure, while the operators have completed checkpoint 2 and they are processing tuples after checkpoint 2 that reach the sinks, a failure happens that kills operator 2, as you can see in the right figure. Looking at the right figure, according to the checkpoint-based approach, operator 2 prime loads checkpoint 2 from the resilient store, and operator 1 rolls back its state to checkpoint 2. Then in the left figure, operator 1 starts processing input data from the offset recorded in checkpoint 2 and pushes its output downstream to operator 2 prime, which processes the tuples and pushes its output to the sinks. But sinks had already seen the first X tuples from epoch 3 prior to the failure. In contrast to operators in the data flow graph, the state of sinks cannot be rolled back in general according to the specification of the output commit problem. It is worth to note that sinks represent external applications consuming the output of streaming jobs. The solution space of the output commit problem features three types of techniques and another two special mentions that do solve the problem practically, but strictly speaking, they don't meet the problem specification. As we will explain, each of the three types of techniques use a different trait of the input or computation to identify whether a certain tuple has appeared again. Transaction-based techniques use tuple identity. Time-based techniques use progress, while lineage-based techniques use input-output dependencies. The first type of techniques uses a transaction-based approach where it checkpoints each tuple or batch of tuples and attaches to it a unique ID. Based on the ID, it can identify whether a tuple or batch of tuples appears again and discard it. In this example, operator 1 and operator 2 checkpoint independently without coordination. Operator 1 also keeps a log of the output tuples that it has sent to operator 2 until it receives an acknowledgement from operator 2 that it has received a certain tuple. Then operator 1 removes the acknowledged tuple from its log. At the depicted figure, operator 1 has checkpointed both tuple number 1 and tuple number 2, while operator 2 has only checkpointed tuple number 1. In addition, operator 2 hasn't yet acknowledged the receipt of tuple number 1 to operator 1. Sadly, before tuple number 2 reaches operator 2 and before operator 2 acknowledges tuple number 1, operator 2 dies as you can see in the right figure. When operator 2 prime recovers in the left figure, it reaches its latest checkpoint from the resilience store, which has recorded tuple number 1, and asks operator 1 to start sending input tuples. Because operator 1 never received an acknowledgement for tuple number 1, the tuple is still in operator 1's log. So operator 1 sends to operator 2 prime both tuples number 1 and number 2. Although operator 2 prime sees the tuple for the first time, it can discard it because the tuple's unique ID is already in its checkpointed state. Contrastingly, operator 2 prime will process tuple number 2. This example reflects the approach of Millwheel with respect to the output commit problem. Another system that implements a similar approach on batches of tuples is Storm's Trident. The second type of techniques uses a time-based approach where operators attach a monotonically increasing timestamp to each tuple according to a logical clock they possess. Based on tuple timestamp and the current time of their logical clock, operators downstream of a failure can discard tuples that have appeared again. On checkpoint, each operator attaches the timestamp of the last tuple that affected the checkpoint. In this example, operator 1 and operator 2 have a monotonically increasing logical clock and attach a timestamp to each tuple as depicted in the figure. In the depicted snapshot, only operator 1 has performed checkpoint 1. The last tuple that affected operator 1's state in checkpoint 1 has timestamp t equals 10. Operator 1 has saved this timestamp in checkpoint 1. In the right figure, operator 1 and operator 2 complete checkpoint 1 and process another tuple when suddenly a tragedy finds operator 1. Then in the left figure, operator 1 prime recovers, loads checkpoint 1, and tunes its logical clock to timestamp t equals 10, according to checkpoint 1's timestamp. Then operator 1 asks the input sources to provide it with input tuples from the desired offset. Operator 1 processes the purple tuple again and attaches to the tuple timestamp t equals 11 according to its logical clock. The tuple is sent downstream to operator 2. Operator 2 discards the purple tuple because the tuple is behind its logical clock. The example resembles the implementation described in one of the SIP system papers. The third type of techniques uses a lineage-based approach where each operator persists input dependencies in the form of unique sequence numbers for each tuple asynchronously. A recovering operator retrieves its input dependencies from the resilience store and asks upstream operators to provide the input tuples that correspond to the unique IDs. Upstream operators may recursively ask their upstream operators until all dependencies are resolved. The recovering operator should mostly receive input tuples that correspond to pending input processing. If already processed tuples are reprocessed by a recovering operator due to the asynchronous pushing of dependencies to the resilience store, then downstream operators will discard those tuples based on their input dependency sequence numbers, which are valid and active. The system removes unneeded dependencies by means of garbage collection. In this example, operators 1, 2, and 3 persist their input dependencies to a resilience store. Then at some point, operator 2 dies. When operator 2 prime is started in the left figure, it requests its input dependencies from the resilience store and asks operator 1 to provide it with the tuples corresponding to those input dependencies. Operator 1 responds with the tuples, and operator 2 prime reprocesses some tuples that operator 2 had processed because operator 2 didn't manage to update its input dependencies to the resilience store before its sudden death. However, operator 3 that receives duplicate tuples from operator 2 prime discards them as invalid or duplicate because based on its current set of dependencies. The depicted technique is implemented in the time stream paper, as well as the stream scope paper with some differences. Another paper for the SIP system uses vector clocks to track dependencies between input and output tuples, which stems from the same idea. Moving on to the special mentions, special sync operators can in some cases retract output. For instance, a file sync can truncate output, and a database sync can delete tuples from a database table. Both capabilities are supported by operators in IBM streams. More generally, any resource that supports versioning can be treated in this manner, borrowing the idea of multi-version concurrency control from the database world. This functionality entails that consuming applications can benefit from this behavior, for instance by checking a dirty read flag that signals that more updates are underway or that all changes have been permanently committed. As mentioned in the beginning, this solution does not address the problem's specification since it assumes that output can be retracted and because it is only possible for certain types of output. Finally, external sinks represent external systems that provide output deduplication, thereby solving the output commit problem. One such representative system is Apache Kafka, which features the transactional sync function. The transactional sync function only outputs data to the outside world when they have been permanently committed, such as when a checkpoint has been completed. This way of solving the output commit problem, although effective, doesn't satisfy the problem in the sense that external sinks are separate systems. So technically, the streaming system has already fired the same output twice. This solution is popular among modern streaming systems such as Apache Flink and the latest structured streaming version of Apache Spark. One way to categorize the solutions provided by special sync operators and external sinks is as optimistic output techniques that push output immediately and retract it or update it if needed, and pessimistic output techniques that use a form of write-ahead log to write the output they will publish if everything goes well until the output is permanently committed. Optimistic output techniques, which resemble multi-version concurrency control from the database world, include modifiable and versioned output destinations, while pessimistic output techniques include transactional sinks and the like. You can read about this distinction in the state management paper of Apache Flink. Closing the discussion of the output commit problem, the streaming systems that solve the output commit problem do so under assumptions. Like Millwheel, IBM Streams does not require deterministic computations, but Streams only solves the problem when its special sinks are applicable, so it's not listed here. According to this table, Millwheel makes the weakest assumptions. TimeStream and StreamScope assume deterministic computation and deterministic input. In addition to the previous, Trident requires ordered transactions. Finally, SIP assumes the aforementioned plus a monotonically increasing logical clock. This concludes our discussion on fault recovery.